everybody. This is my first virtual lesson for you guys. I wish we could be in normal class, but here we go. So the next part of what we were going to do, we're actually going to combine some of the stuff we were doing with derivatives with some of the stuff we did in the past. So this first slide is just kind of a reminder. We're actually going to be able to use the derivative to find any of the extrema, which were minimums and maximums of the graph. I'm not going to make you look at the graph, so we're just going to do most of this by hand. There is a little graphing element that we could do, but we're not doing that for this. We're just going to find the values that they could potentially be. So I'm not necessarily going to ask you to label them as a specific minimum or maximum. So these are the choices we have. We have two different absolutes. This book uses the word local. We also called those relative in the past. But we're asking for extrema. Those are critical numbers on the graph, which we can actually find using the first derivative. Okay. Alright, so whenever you're asked to find derivatives, remember derivatives were slope. Okay, so whenever we found the first derivative, we were finding the slope of the curve. And so the values of those slopes were actually the values of slopes of little lines as you go along to it. So that's why occasionally I'd ask you to write an equation for a tangent line, and what it was tangent to that specific point that I gave you on that graph. And so where we're trying to find extremas are the minimums and maximums. So if you put a point on the minimum and maximum of your graph, the tangent line is actually going to have a slope of 0. So if you look, for instance, at this graph I drew, so say this was our original equation, and we wanted to find the slope right here at this maximum. Well, if you put a little line across that, that's going to have 0 slope. So what that's telling me is that the slopes at the maximums and the minimums are going to be 0. So what we can do is we can use the first derivative and set up a little equation for ourselves to be able to find where that occurs. So what we're going to do is we're going to take the derivative of the function, and we're going to find where it equals 0. So whatever you get for your derivative, we're going to set it equal to 0, and then solve it like we would any other equation. So we're going to solve it and find x. Now sometimes the graph might be where the graph's undefined. So like when you have to use the quotient rule, we have the bottom part of that. So we'll find when x equals 0. So sometimes that's another place where it's a critical number. But again, what we're going to end up doing is take the first derivative, set it equal to 0, and solve for x. So we're going to combine a little bit of our derivative stuff with solving from the past. So let's do a couple of examples. So for the most part, we're going to be looking at pretty straightforward examples, mostly just power rule that we have to work with. I will do one that have the quotient rule because, like I said, sometimes when we work with fractions, there's a couple different things we have to do. I think there's a chain rule in there too. So we're going to do several examples of different varieties that you can see. So here's our equation. Again, don't worry about graphing it, because before, the way we'd find extremas, we'd graph it and we would look at our decimals and find the extrema that way. Right now I'm not worried about that. I'm worried about how we can use the derivative to help us find those. So our first step, take the derivative, just the first derivative. So power rules, take the 3, multiply it by the 2, so we have 6x, subtract 1 from the exponent. So the derivative of 2x cubed is 6x squared. And we take the derivative of negative x squared, so it's going to be negative 2x. The derivative of 5 is 0. So there's our derivative. So that's our first step. Second step, we need to set the derivative equal to 0. So we're going to take this part and make a little equation for ourselves. Set it equal to 0. Okay. So whenever we have quadratics, the biggest way we solve those is by using a little bit of factoring. Okay. So this one we have to factor a little bit. Now it's not the trinomial factoring where we do what multiplies the last number adds to get the middle. We'll actually see an example of that later. But this one, we have to use the type of factoring where we have to take out what they have in common. So we're going to do GCF factoring, kind of like we did with limits. So we're going to look at what we have. And again, we're trying to solve for 0. So we need to get x by itself. So since I have 2 x's, I have to kind of narrow them down. So I'm going to look and see what they have in common. So the greatest common factor between 6 and 2 is 2. And then they also have an x in common. So I'm going to take that and pull it out in front. So that's my GCF. So then I divide it out of those terms. So I take the 6 and divide it by 2, so that's where I get 3. And then I take my x's, take an x out of x squared, I have a single x left. Divide that, 2 divided by 2 is 1. And I took the x out here. So that was GCF factoring. So hopefully you guys remember that. We've done it a lot in the past. So we took out what was in common. So now to solve it, we take everything that has an x, get set equal to 0, and solve for it. So we actually have 2 things to solve now. We have the 2x and we have the 3x minus 1. So we take 2x, set equal to 0, basically set everything equal to 0. Solve for x, divide by 2, we get x equals 0. So there's one of our answers. And then we take our 3x minus 1, set that equal to 0 as well. Add 1 over. We got 3x is equal to 1, divided by 3. So x is going to equal 1/3. So there's our second solution. So both of these would be where the extrema occur for that function. So both of those have a slope that's 0. So there's a slope at 0 at 1/3, and there's a slope of 0 at 0. And that's all I want you to find. So you take the derivative, do a little bit of factoring sometimes. You don't always have to factor it. Like there's no square and not an x here, then it's a pretty simple one. So there's sometimes where you just get one answer. A lot of times we do end up working with quadratics, and you should have 2 answers for that. So let's do that one. I'll give you a minute to look at that or a couple seconds to look at that. You need to pause it, rewatch, so you can follow along with me. So let's go ahead and do the second one. Again, first step, take the first derivative. Second step, we're going to solve it. A lot of times with these, you do have to factor, so we're going to use all kinds of factoring with this one. So take the derivative. So the derivative of 2x cubed is 6x squared. The derivative of 3x squared is 6x. The derivative of 12x is negative 12. The derivative of 5 is 0. Okay. So now we're going to take that first derivative, set it equal to 0. Okay. So with this one, when we have 3 different things, it's actually a trinomial. So we are going to have to use that idea that I kind of mentioned. Let's do it multiplies to get the last number, adds to get the middle. But we actually have to do a little bit of things to fix it. So if you look, can I simplify all of these terms? I sure can. So what you can do is if you look at them and you notice you can divide by that, you can go ahead and do that. That's actually part of the GCF, so I'm actually going to use a little bit of what I just did. So since they all have a 6 in common, I'm going to pull that out in front. So that's going to go down to just x squared, that'll go down to x, and that'll go down to 2. Okay. Now when I have 3 things like this, when I'm factoring, whenever I have to factor this a little bit more, again, just ignore the 6 for just a little bit. So I can, again, as long as I have 2 types of x's, I have to factor a little bit more. So this is where I have to do trinomial factoring, where I do what multiplies to get the last number, adds to get the middle. Again, each factor has an x, that comes from the x squared. The only factor of 2 is 2, so it has to be 2 or 1. And the way I can multiply to get to a negative 2 and a positive 1, if I make 2 positive, 1 negative, and I have that completely factored. So I use a little bit of GCF to simplify my terms. So if you notice that they all have something in common, you can take that out. So that's what we did with the 6, we just divided that out. And then once it has 3 terms, then we use our trinomial factoring. We multiplies to get the last number, adds to get the middle. Again, we really couldn't do that at the first because we have 12. And also we have a 6 here, that creates a little bit of an issue for that. Okay, now we're going to set everything equal to 0. This one we can basically ignore in the future, but like I said, since we technically had set everything equal to 0, I'm going to go ahead and show that with this example. Does it really make sense for 6 equals 0? No. So this one's not going to give us any solutions. But like I said, technically we had set everything equal to 0. So we set the next one equal to 0. and solve. So we got x is equal to -2 as one of our answers. And we set x minus 1 equal to 0. So we get x equals positive 1 as our other example. So these two things are our extreme. So if you have any questions, please ask me via email. Feel free to pause and rewatch this as many times as you need. Alright, now we're going to do, I think 2 more examples is what I have. One uses chain rule and one uses quotient rule. This one looks a little scary, but it actually turns out not to be too bad, and I'll show you why in a second. So, we have to use chain rule, because again, we have that stuff inside the parentheses raised to an exponent. So whenever you see that, chain rule. So to do the chain rule, the number comes out in front, so the 1/3 will move in front of that. The stuff inside does not change, it'll stay 4x plus 5. We do subtract 1 from that exponent, so we get -2/3 when we do that. And then we have to take it times the derivative of the inside, which the derivative of the inside is just 4. Okay. So now I have to set that equal to 0. Okay? And I know that looks really ugly, but I promise it actually works out in our favor. And actually there's some things that you can end up skipping here in a second. So we're going to take that 1/3 and then 4x plus 5 to the -2/3 times 4 equals 0. Okay, so whenever I'm solving something like this, you kind of start from the outside and work your way in. There's actually 2 choices you can start with. To get rid of the 1/3, what I can do is kind of multiply by the bottom. So if I take 1/3 and take it times 3, that's going to get rid of that 3. So I'm going to multiply that over here. But what happens when I take 0 times 3? It's just going to be 0. Technically, I still have this 1 left, because that really doesn't really change much for us, because if we divide by 1, again, it's not going to change anything. So I'm actually going to get rid of that 1. And again, still equal to 0. So we got rid of the 1/3 by multiplying by its opposite, which is 3. The next thing I need to take care of is this 4. Since it's being multiplied, I can divide it. Which again, what's 0 divided by anything? It's just going to be 0. So I have this 4x plus 5 to the -2/3, and that equals 0 still. Okay? So you should start noticing a little bit of a trend. Okay? So the 1/3, that didn't change anything over here. The 4, that didn't change anything over here. Now we have this ugly exponent. The way we get rid of that ugly exponent is we actually use the reciprocal exponent. Okay, so instead of -2/3, we can use the -3/2 exponent. But like I said, that's kind of ugly, but that's going to get rid of that exponent here. But again, now we've used that reciprocal. What's 0 raised to the exponent? What's just 0? Okay, so what we boiled it down to is this. All that outside stuff that's kind of ugly and scary to move, we ended up just having to multiply to 0, or divide by 0, or divide with 0, or raise an exponent to 0, and ultimately it just ended up being 0. Okay? So kind of the moral of the story here with this type of an equation, whenever you have a bunch of crap outside of something raised to an exponent, ultimately all that stuff is going to end up going to 0, and so really all you have to do is take that inside stuff and set it equal to 0 and solve it really quickly. Okay, so we actually are going to only end up with one answer. So like I said, I wanted to show you the whole thing so that way you can see why that's happening. But whenever you have all this stuff outside that you have to either move by multiplication, division, or exponents, when you raise a 0 to an exponent, divide 0 by anything, or multiply with 0 by anything, it ultimately ends up with 0. So the only steps that really matter are the stuff that's added inside. Okay, so just keep solving. I'm going to subtract the 5 over. So we got 4x is equal to negative 5. And then I divide the 4. So my extrema here is negative 5/4. That's the only extrema that I have. Oh, yeah, one more. Okay, we got a little bit of a quotient rule with this one, and then we'll be done. Okay? Again, I know it's quotient rule, so I see the division. So, the way we do quotient rule is the derivative of the top, so the derivative of 2x is 4x, times the bottom as is. And I will simplify that in a second. And then we subtract the derivative of the bottom, which is just 1, times the top as is. And then it's all over the bottom square. Okay. Don't forget that bottom part. Okay, we can't forget about all that. I am going to simplify that a little bit. You should with whenever you're using this. So I have to distribute the 4x. So you have 4x squared plus 8x. And then this becomes minus 2x squared. So the top we can combine like terms. So the top we have 2x squared plus 8x, and the bottom is x plus 2 squared. Okay, so here's where we get to a little bit of a unique thing when we set a fraction equal to 0. We actually have to set both the top and the bottom equal to 0, because both of those are going to give us critical numbers. So we're going to take the top part, set that equal to 0, that'll give us some extrema, and also the bottom part will give us some extrema. So once you have your quotient rule all finished, take whatever you got for the top, we're going to solve that, e set equal to 0, take whatever you get to the bottom, solve that, take that, set it equal to 0. Okay, so the first one, again, this is like a lot like our first example. So we have to take out what they have in common. So they both have a 2 and an x. So we have to factor out our GCF. Divide that out. So 2 divided by 2 is 1. Take an x out of x squared. It's just a single x left there. Then you take 8 divided by 2, which is 4. Take an x out of there, which is nothing. Okay, then you set everything there equal to 0. So you have 2x equals 0. So x is going to equal 0. Then you have x plus 4 equals 0. So x is going to equal negative 4. So there's our second one from that one. Now this one we have to solve. Having greater squares, you have to square root it, okay? So we can square root that whole thing, okay? All it's going to do over there is get rid of the square. So it's x plus 2. And then what's the square root of 0? It's just 0, okay? Like I said, whenever you have stuff inside parentheses with exponents like that, when you set it equal to 0, it actually works out pretty nicely for you. Because really all we have to do is say x plus 2 set equal to 0. So you subtract the 2 over. So our third extrema is negative 2. So I hope this was helpful. I wish we could all be together and not doing this with a video instead, where I could just be teaching you in class. If you have any questions, please let me know. Like I said, you can email me. I'm going to be setting up some online support for you to jump in with an online chat with me, so you can ask questions. With the video instruction, I will post a copy of my notes, and then I'll also post like a little assignment with it too. So please let me know if you have any questions. I miss you all. I wish we were here together, because for you, my seniors, I don't want the year to end this way. So thank you. Bye.